Hello everybody, this is Jim Corkins, and we are going to begin with the first part of electric fields. So this is electric fields introduction, and what I'd like you to do, if you're in Physics 101 or Physics 112, please read OpenStax Chapter 18, Survey Chapter 15, or Coletta Chapter 17. If you're in Physics 131, please read OpenStax Chapter 5 or Night Chapter 26. So this is going to be linked with the sapling homework number 3 if you're in Physics 112 and homework number 3 in Physics 131. Also, we're going to be doing Lab 3 in this, and there's 2 parts to that lab. The first part is just about electric fields, and the other one is about the consequence of electric fields and how it gives rise to a force. So, all right, let's move on. So the overall topics that we're going to cover is the electric fields model, the electric fields due to multiple point charges. Also in the electric fields model, how do you quantify an electric field? But this is going to be about the directions as well. The electric fields of multiple point charges, so how electric fields interact with other electric fields. And that also gives rise to what is a parallel plate capacitor. So what you'll have is just a horizontal line of positive charges on one side and a horizontal line of negative charges on the other side, and how and what is the consequences of having this perfectly uniform electric field. We're also going to do the motion of charges in an electric field. We're going to touch on the motion of a dipole in an electric field, how it twists and turns, and how it could cause a torque. Then we're going to move on to, if you're in Physics 131, we're going to move on to continuous charge distributions. And that will be on a line of charges, a ring of charges, disks, planes, and also spheres of charges. Okay? Right. So here is the basics of the electric fields. And these are the overall rules for drawing the electric fields. When you have, so we'll talk about these also as we're doing problems in this. We'll talk about the first one, the density of field lines means a stronger field. That means when you have field lines, electric field lines close together, that means the electric field is going to be at the strongest at those points. Okay? So that's that. When they're further away, they're going to be weakest. All right? So that has a consequence on a great force and a weak force is based on a strong field and a weak field, right? So those density of field lines have consequence based on how charges interact with other charges. The field is always going to be a tangent to the surface of whatever is causing the field. So if you have, essentially this, if you have a sphere, the field lines are going to be emitting radially from that surface, right, at a perpendicular to that surface, right? So almost like a spokes on the wheel, right? So field lines, number 3, field lines emanate from positive charges, and then they point towards negative charges. So electric field lines are pointed radially away from positive charges, like spokes on a wheel. And imagine a negative charge with little arrows pointing towards it from all directions radially. And that's what field lines look like on negative charges. The number of field lines entering or leaving a charge is proportional to the magnitude of charge. So again, more field lines, more charges, right? So more field line, more charges creates more electric fields, and that means also denser electric fields. Field lines never crisscross; they always join. Okay. So here is so we're now going to talk a little bit about that, but we also now have an equation to deal with. Okay. And we have an equation that quantifies electric fields. and you kind of recognize much of it. So what we have is, so what you're seeing here is a negative charge, and notice that the electric field lines are pointed towards it in all directions and almost radially, as if they're tangents to the surface. So the surface is a circular surface, so these electric field lines are pointed towards, at a perpendicular to that surface, or radially out, or radially inward towards the negative charge. Okay. If it was a positive charge, which I'll show you in a second, these arrows would be on the opposite side. They would be pointed outwards in all directions. Okay. Now the electric field is only caused, so this negative charge is creating an electric field. Okay. So non-contact forces that we studied earlier, the Coulomb force is a non-contact, just like the Earth's, similar or analogous to the Earth's gravitational, to a mass's gravitational field, right? So all non-contact forces are emanated due to a field, right? So that's how the Earth can pull you. You jump in the air, you're jumping off a cliff into water. The Earth is pulling you down towards it, and your mass and the Earth's mass, your mass is creating a field, a gravitational field, and the Earth's mass is creating a gravitational field. And it's the interaction of these two fields which allow it to actually interact with you but not physically touch you. And so the same thing is happening here. Okay, so how a positive and negative charge, or a negative and negative charge, or two positive charges interact with each other without touching each other is because they're really, what's going on is their electric fields are interacting with each other. And they take on that form. And you'll notice, since there's only a negative charge, there's only one Q here. If we were dealing with if we're dealing with a force, okay, so the Coulomb force, which you know up here is going to be F, and that's the Coulomb constant, Q1, Q2 over their distance apart squared, right? Well, in this case, we're only looking at the field. So we only want to look at what is causing that field, right? So we don't really care about this other Q2. We're basically tossing that out. And when you toss it out, now you're not dealing with a Q1 interacting with a Q2. You're only looking at a Q1, which then it just becomes an electric field, right? So now you're just looking at the electric field. You don't care about this Q2 right now. You'll worry about it later on when you actually want to calculate a force, okay? So that's why you only have a Q1 here and not another Q2, because we're taking a look at the electric field and not the force. Also, just like the Coulomb force, the distance apart squared is still in effect here. So the fields, you'll notice, like the gravitational force, the force due to the Earth's gravity is equal to capital G1, and one mass interacting with another mass all over their distance apart squared. That's a similar kind of equation to this, right? And notice that this force is dropping off by r squared. That means the Earth's field, if we were to throw this out, now we would have basically kind of like the gravitational field. So anyways, so the Earth's gravitational field. So I'm going to make something up here. Anyways, we would be just dealing with the Earth's gravitational field if we tossed out the person. So now you'll notice the Earth's gravitational field drops off by 1 over r squared. Well, the same thing's kind of happening here with the electric field. It's dropping off by 1 over r squared. So that we're still going to have to think in terms of that 1 over r squared. Superposition principle shows that basically when you have interacting vectors, that they're going to sum each other, right? So really, the electric field is a sum of vectors that are interacting with each other. And so they're going to be represented by by single vectors. And I'll show it to you. Typically, when you write these, you'll write these as one long vector, not these small short vectors. Okay. And so these vectors are going to be pointed inwards in all directions for a negative charge. So notice the vector heads are pointed towards. So you wouldn't have these like little piecemeal dots of vectors. Really, you have one large vector, and it's a superposition type of situation where the vectors are adding up. Okay. With positive charges, the electric field, the vector head is going to be pointing outwards in all directions. Okay. So I also put a link here to the simulation that's hosted at Mesa Community College. All right. And let me go ahead and bring that up. So this is going to be a part of the very first lab, which is I think third activity in 2.0. And so here's how it works. And I'm going to use this to actually show you how it works, but also what the electric field looks like due to a positive or negative charge. So I'm going to click on here, click on charges, and it brings up a host of charges that you could select from. I'm going to select a positive 8 microcoulomb charge. And I'm going to place it right here. All right, and let me zoom in. Oops. So zoom in a little bit. Now if I click on field vectors and I click around it, it's going to show the field vectors at different points. And notice that the field vectors get shorter and shorter the further out, just like in that actually, let me click. I'm going to try to, you got to be careful on how you click this, but the length of these arrows shows the electric field strength. So a shorter vector would be a weaker electric field. A larger vector would be a large electric field, and that's due to the 1 over r squared drop off. So I'm going to show electric field here. Click here, and notice how it gets a lot weaker. And let me try it here and here, similar to this one. I'm going to try to get this right in a line with this. I should have taken more time. Darn it. I wish you could clear. Yeah, you can only clear the entire thing. Darn it. Let me try to move this and center it. Make it easier for me. It's good for you to see me make mistakes when I do this. That's what I tell myself. So I'm trying to be very close with how I click on those vectors. And what I'm trying to do is show it to you in all directions at about the same distance. It's almost up and down. Right? So this is kind of what we were seeing before in this with the little piecemeals. But really, how we really draw this is we use electric field lines, not so much the vectors. The vectors I like, there's a purpose for the vectors. They show the magnitudes, right? And they can show how the electric field drops off, right? But typically, you click here to draw the vectors, and they're usually represented as a solid line. I'm trying to click right where I clicked before. I'm not very good at it. And they're not drawing vector heads on these field lines, but notice that there is pointing radially away from the object, okay? and that the vectors, the field vectors, are pointed outwards. So this is a positive 8 microcoulomb charge. Okay, I'm going to clear this. I'm going to click on charges, and I'm going to select actually I'm going to clear everything. I'm going to select a negative 8 microcoulomb charge and try to place it right here at the center. Try to do my best to center it. Now I'm going to do the same thing I did before. Click on field vectors, and be careful because the field vector is going to be pointed towards this. And notice how the length of those vectors are dropping off by 1 over r squared. Maybe do a couple so you can see how it's decreasing. In size. Whoops. Well, I'll let that one go. Always mess things up at the end. Anyway, so again, notice the field vectors are pointed towards it, and these two are again dropping off in magnitude the further away you get, and that drop off again is by 1 over r squared. But again, we would represent these with just solid lines pointed radially away from it or towards it. In this case, it'll be towards it in all directions, right? And there would really be millions of these. It kind of, if I were to really try to get every bit of this, it would look insane. All right. Well, I hope this was helpful right here. And that's basically how you draw electric field lines. And again, the electric field lines are going to be tangents to the surface of the object. So in this case, it looks like spokes on a wheel. So the surface is circular, so that those tangent lines are going to be pointed outwards in all directions. Okay. And here's another way of seeing this. Now this is a case where I wanted to illustrate how how increasing the amount of charge will also increase the the electric field line densities. Okay, and if you wanted to try to replicate this, you could try it out by clicking on that link and trying it out. But essentially, here's what's going on. If you just dragged a negative Q out, and you clicked here, this is a good representation of how we would draw electric fields, right? And it's a conceptual model too. And so if this is the exact electric field for a negative Q charge, well, if you put two negative Q's out right on top of each other, okay, notice that the electric field line density has increased. In fact, it has exactly doubled, right? And that is because over here, this is represented, this electric field is going to be K times a negative Q, and that's a negative 1Q, I should say. Negative 1Q all over R squared. So if I chose a distance right here, this would be the distance apart, R. Right, so the electric field line at this point, or the magnitude of that electric field at that point, I got to put that absolute value, would be represented right here. Well, over here, at the same distance out, so this is going to be distance R away as well. Well, this electric field at this point, you'll notice this distance from here to here is very large, right? So I kind of look at things about at this distance here, this is also a distance r, right? So if I took a slice right through here, well, actually, through both these lines, I drew a line through both of these parts, and I measured from here to here. Notice that there's only two lines, well, actually, yeah, two lines encapsulated by this. Well, at this distance here, and this distance is also r, and I'm just kind of drawing a radial line through this. Well, now you have about twice the electric field lines going through this, right? So look at the density of this. This distance from here to here, right here, it's got extra lines. So this electric field would be represented by K, and then now we've doubled the charge on that over r squared, right? So by doubling the charge, you're doubling the number of electric field lines. Essentially, it's saying the same thing, right? And so that's how we represent it visually, is we basically, if we represent a 1Q with, what is this? It looks like I'll count 1, 2, 3, 4, 5, 6, 7, 8 lines. Over here, we would have 16 lines, okay? And so that's how we're representing this equation visually, okay? And just again, notice like the density of field lines at this distance r away right here is not very dense, but over here it's much more dense. In fact, it's twice as dense, right, at a distance r away. So that's also what you're kind of representing as well. All right. So the vectors, so the electric field lines are going to be, so you have electric field lines that are kind of bending like this, okay? And so the field vectors are going to be at little tangents to that, right? So they're going to be at little tangents to each one of those points, right? So if you had a point right here, what is this field line is kind of going, at this point, it's the slope at that point, right? So you've got the little field vectors, right? I think I made a mistake talking about tangents earlier. It should be perpendiculars to the surface, but here's what I meant by that. So you have the electric field lines right here, and notice if you took a dot here and took a dot here, and you look at the slope here and the slope here, the field vectors would be at tangents to those, okay? And here, if you took a tangent right here, it would just be, you know, pointing along the line vector. But here's a good representation of, here you've got field lines, so you've got little vectors pointed out in all directions, and notice those vectors are getting weaker and weaker and weaker. The length of those vectors are getting smaller and smaller and smaller, right? And so this is probably something where I don't think there's only just these three field line vectors, but it's probably zoomed in on something out here where there's probably another charge out here, like a negative charge. And we'll talk about how you draw electric fields due to interacting charges. But this is probably an electric field where there's actually multiple charges interacting with each other, and that's why it gets this weird kind of bend to it. It's not emanating radially from a surface like this. This over here is a capacitor, okay? And I want to point out the difference between this and from a single charge and also this, because this positive is right here, and you have another positive, you have billions of positives that are built up on one plate. And for a capacitor, what that means is that negative charges are going to automatically build up on another plate. So when that happens, all these little charges, for every positive charge, you have a negative charge, right? And then here you have another positive, you have a negative charge. So what happens is this radial electric field in between here begins to actually get bent. And so now if you'll notice, the field lines are pointed straight across. And what that means is, notice that the field line here is more dense than out here. So for a single positive charge, you've got the density is greater here, closer to it than later here. But notice that the field lines here are equispaced no matter where you are on this, right? What that means is that a ideal capacitor creates, so this capacitor right here, which basically is a conductor with just two conducting plates, again, creates a constant electric field. This electric field is not constant, and it's actually governed by this. Okay. With a constant electric field, you have to determine, you can't determine the electric field here so if there's a distance r right here from this positive, then you have a distance here from that negative, but then you have another positive at this point, and then another positive at this point, and then another positive. It becomes impossible to actually calculate the electric field using the Coulomb equation electric field, right? So what you have to do is that you have to solve it a different way, and we'll talk about that later on. But right now we're just concentrating on this, but I wanted to point out that with a capacitor, the purpose of a capacitor, one of the purposes is to actually create a constant electric field in the center, okay? So that is an ideal capacitor. So again, here's the rules for drawing electric field lines. We're just kind of bookending those rules that I showed you before. You're going to always draw field lines that are continuously curving, right? And the density of the electric field lines are going to be the density of the field lines are related to the magnitude of the electric field. Also, those field vectors are the magnitudes represented by the length of the vector. It's going to be pointed away from positive charges and towards negative charges, and field lines never cross, right? Again, they'll join up. Right, so if you have a dipole, and a dipole, typically when you call a dipole, means two poles, right? And that could be a negative or a positive and a positive, or a negative and a positive. Typically when we talk about dipoles, it's usually talking about a positive and a negative. But when you have multiple charges, all right, if you have I'll zoom in on this a little bit so you can see it. If you have a positive charge and a negative charge, they're going to be interacting with each other, and it kind of looks like two spiders sort of trying to give each other a hug. And so these lines are actually a vector additions going on, right? So for example, right here at this point, I'm going to draw a point right there. The field line vector at this point right here would be pointed away from the positive, and this field line vector would be pointed towards that negative, right? And since it's the same distance, this distance r is equal to this distance r, so you do that field line vector right here and right here, and by adding those two vectors, because its superposition takes place at this point, I'm going to take the down and to the right vector, add it to up and to the left, and what the resultant vector is going to be straight across. And I should actually use a different color to represent that. So the sum of those two vectors creates just a straight line and a cross vector. So at this point right here, really, those two black lines would be added together just to create a longer blue line, because it's superposition that takes in place. You're summing the vectors of these two. And so that's what happens. At this point, you'll notice the arrow is straight across. Same thing is happening. You're going to have the positive charge is going to have a vector pointed away from it. And the negative charge is going to have a vector pointed away from it, right? And so adding those two guys up, you get a much larger blue vector pointed to the right. So you have a positive charge, the vector is pointed away from it. A negative charge, the vector is pointed towards it. Add those two vectors up, and you get one long blue vector, right? Over here, at this point, actually at this point right here, the positive charge is going to have a vector pointed away from it. The negative charge is going to have a vector pointed towards it. And I should choose, maybe I'll choose one on right here. So why is this curved this way? So if you notice, this guy is a little bit off center, so it's going to be pointed away from that positive charge, and this negative Q is going to have an electric field pointed towards it, right? And so now you got to add those two vectors together, and I'll try to do my best to. That's a positive one. Add this up and right towards the negative one, and what you get, and I drew that negative one to be a little bit longer than it should be. And what you get is, by adding those two together, is you get a sum of vectors that is pointed down and to the right. Well, that's why you get this pointed down and to the right. So again, these are just the sum of vectors. And what I'm doing is kind of using, I'll be doing something like this too. So I got a positive 8 charge here. I'm going to grab, actually that was a negative 8 charge. I'm going to grab a positive 8 charge. And I'm going to try to be consistent with this. Grab the negative 8 charge and center it over here. And so I'm going to draw the field vectors. At the center of this, if I draw a field vector, it should be pointed away from the positive. Here, the blue is the positive, the red is the negative. So pointed away from the positive and towards the negative. That means that field vector should just be pointed to the right. Notice above it, if I point it above it, back to this, you got the pointed away from the positive and towards the negative. Add those two vectors up, and then you get a sum of vectors, a superposition vector pointed just to the right. And so this should be just to the right as well, but weaker. And same thing here, right? So if I also take, I'm going to try this dot right here, which I think we said the sum of the vector should be kind of down and to the right-ish, and notice that's happening too. Well, if I draw the field lines at these points, if I click on the field lines at these points, notice that they're connecting each other. All right. And then out here, it starts to take on that look. So now it's beginning to start looking like the drawing from the PDF, right? Notice the one right next to it. Now if you have positive 2Q, okay, the positive 2Q has double the positive lines emanating from it, and this is just a negative 1Q. Well, those field lines are joining up as well, right? And notice it's very kind of disproportionate looking. This one looks very proportional. The number of field lines here is equal to the number of field lines here. Here we got twice the number of field lines leaving, and then this is the negative Q has less field lines coming into it, right? So what's happening is that this electric field over here, due to these guys, is going to be disproportionate. It's going to be more dense on one side than is on the other. Well, this one is perfectly proportional and symmetric as well, right? If you have two positive charges or two negative charges, so if we have two positive charges and they're both the same magnitude of charges, notice something that's really interesting, right? So it looks like this space right here, there is nothing going on. Well, what's happening is this positive charge on the right, is going to have an electric field pointed to the right. This positive charge here on the left is going to have an electric field pointed away from it. And the positive charge on the right is going to have an electric field pointed away from it as well. Well, add those two vectors together. You have a right vector added to a left vector. Well, the overall vector right here, if you're going to do that, if you add those two vectors, you take a step to the right and then you step to the left, you started and ended at the same place. That means the electric field is 0. So all here, this space right here, and actually along this line right here, the electric field is actually equal to 0. Let me do this. So this, along this dotted line right here, along that dotted line, the electric field is 0. All right? And again, this is happening because those field vectors are adding up and then eliminating each other, right? And this looks two positive charges or even two negative charges. The positive charges, the electric field is pointing away from them. The negative charges, the electric field is pointed towards them. But they're kind of avoiding each other. Okay? And so this negative electric field is this interaction of these two, I shouldn't say negative electric field, this interaction of these two fields is what's repelling it. When the two fields are joining, okay, notice the two fields up here with the positive and negative are joining together, right? And that's an attractive electric field. But when the two electric fields actually look like they're pushing away from each other. And the same thing is kind of happening here with the negative. This is a 1 negative and this is a 2 negative. Notice again it's disproportional, and you'll still have that space of a 0 electric field along that line right there. Right, it won't be at the very center. It'll be actually a little bit shifted. It'll be a little bit shifted towards the negative here. Right, if this is the center space of if this is a distance r here, and this is a distance r here, the electric field will be. Anyways, my point is that you'll have twice the number of electric field lines coming into this 2 charge here on the left, and a negative electric, and then just 1/2 the number of electric field lines for the just 1 charge, right? And so these again look like they're pushing away from each other as well. All right, so that should be at 100%. So I hope that kind of helps you understand electric fields a little bit. And this is dipoles. This is essentially, dipole is a fancy word for multiple charges, right? And it could be a positive or a negative or a positive negative. But usually when we're talking about dipoles, we're talking about positive and negative. So I talked a little bit about how the electric field will follow the shape of whatever is creating, and I think I inaccurately said tangents. Although I guess it'll be perpendiculars to that surface, right? So the electric field line is going to be at a perpendicular to that surface. Actually, I was accurately saying that this is a tangent to that. So the surface is a tangent to the electric field. So I get a little nervous when I do these recordings, sorry. But my point is that the electric field line is going to be perpendicular to every point on the surface, right? And so if you have a weird shaped surface, kind of like this teardrop, sometimes that shape in this case, notice that the electrons, you know, they are not equally spaced, right? Since the shape is going to determine the spacing of the electrons. Well, there's going to be more of a concentration of electrons at the tip, right? Which then means the electric field here. So if I mark out a distance away from here, a distance r away, right there, and I try to take that same distance, okay, I'm going to take that same distance here, and this is a distance r away. Notice that the electric field lines here is way more dense near the tip than it is from the gradual surface, right? So the surface of any conductor is going to determine a lot of stuff. It's going to determine the charge density at the surface, right? Which that is in turn going to determine the electric field density at any distances out. If it's a nice smooth surface, well, the electric field lines are going to be emanating, again, equally spaced radially, right? If the surface is a conductor, a capacitor right here, well, that flat surface is going to make the positives equally spaced with each other and the negatives equally spaced over here. So then you're just going to, the tangent line to the surface here is going to be equally spaced lines, right? So the charge density here is uniform, okay? And so that is going to create a uniform electric field, okay? But let's talk a bit about this here. At the inside of any conductor, the electric field is going to be zero. And essentially what's happening is this positive right here is going to create an electric field pointed down. This positive over here is going to create an electric field out and out and out. This positive is going to create an electric field up. So basically, when you add all these vectors together, it creates the electric field as zero, right? So inside any conductor, okay, all these positives, like this positive over here is going to create an electric field down to the right. If you take this sample vector at this point right here, it's going to have a vector down to the right. This positive over here is going to create an electric field just to the left. This positive over here is going to create a vector to the right. And so that vector plus that vector is going to be zero. So what happens is all these charges are adding up to an electric, and when you add all those little vectors up, they add up to zero. And so that's why the electric field inside of a conductor is zero, right? Okay, and that's an important point. So that's kind of why if you're in a parking garage or you're in an elevator, okay, and the elevators are metal, and you lose reception, right? Because there's basically the electric field outside, the charges are building up on the actual, the field outside is working, but then when it hits on the inside, they all kind of add up, and the charges build up on the surface of the elevator, and they kind of add up to zero. So this is like the surface of the elevator, and the little charges are trying to move up and down. Well, when they're doing that, the electric field is zero on the inside. Okay? So, point of conductors with electric field is that the electric field is zero inside a charged conductor, okay? And that any excess charge is isolated, resides entirely at the surface of the conductor, right? Because that's what a conductor does. and that those electric field lines then will create perpendicular, the electric field lines will be perpendicular to the surface everywhere. Okay? So that's kind of the rules of conductors with electric fields. Not only that, if there's sharp surfaces, the excess charges will accumulate at those sharp areas, and it will then create a more dense electric field versus a smooth area, right? And so with parallel plate capacitors, right, you have a uniform electric field on the inside. And that electric field is equal everywhere since the electric field lines are equally spaced, right? So here we are. We're going to do some exercises, and basically what we're going to try to do is identify the electric field at each one of these points, A, B, and C, due to Q1, Q2, and Q3. So this is just a 1Q here, this is just a 1Q here, and this is 1Q here. So what I'm going to do is I'm going to use different colors. I'm going to call this our blue Q, our number 1Q here. This number 2Q is going to be red. I'm going to use these colors to differentiate my vectors at each one of these points. And we're going to have a green Q, right? And I'll draw, and then I'll draw a black Q for the superposition or the sum of those electric fields, okay? So for example, Mark, this is again the tutorial 2.0 on electric fields. Mark has created an example. So for example, he was saying that at point D, you've got the green Q is creating an electric field pointed directly away from this positive Q. The red Q, which is directly above point D, is going to have also same size vector as a green Q, and it'll be pointed away from that positive Q, but so in this case it'll be straight down. Notice the blue Q is further away from point D than either the red or green. So he's giving it a smaller vector right here. All right. Well now, so basically that's what you're supposed to do, is just draw those vectors out. Okay. I would also be in the habit of what I also am asking you to do is, what is the direction, which is the last one, the net direction of every single one of these vectors. And it doesn't matter the order at which you add the vectors up, but you do have to add the vectors up, and you're going to draw that overall sum of vectors here as well. And I'll use black to represent that. So I'm going to start off with red, the red vector. And the red vector is pointed straight down. And then I'm going to add to that the green vector, which is pointed to the right. And then I'm going to add to that green vector a blue vector, which is pointed down and to the right. So I'm just adding those vectors together, tip to tail. And now the resultant vector, if I started here, I walked straight down 2 steps, I walked to the right 2 steps, and I walked down and to the right 1 step. So I started here, and then I ended right here. I finished right there. The resultant vector goes from very start to very finish. So this is going to be the resultant vector at this point, and it's going to be a long black line. So that is the sum of vectors at that point right there. Okay? And so that's kind of what you're supposed to do for A, B, C, and D. Okay? We'll do one more on this. I'll do I'll do A on this to further illustrate how to do this problem. So A is really close to blue, so I'm going to draw a large blue line pointed away from A. And green is also the same distance to A that blue is. So that's going to be pointed away from the green guy as well. Now, notice the red charge is really far away, so I'm going to draw a small red vector kind of directly away from that guy. And so now I have to, once I've done that, I'm going to just check it, and it looks pretty good. I maybe drew green a little bit longer than blue, but so I'm going to add those vectors together now. So I'm going to start off with a red vector now. Just a little bit different. Red vector is down and to the left, and it's small. I'm going to add that to the green vector, which is going to be up and to the left, really long. And it doesn't have to be perfect, but try to be consistent. And then I'm going to add to that a down and to the right blue vector. Okay? And so that looks pretty consistent with those lengths. Now I have to draw the black vector, the resultant vector. So I started right here. I'm ending right here. And it's going to just be kind of off-center and really long. So the resultant vector is going to be a little bit off-center of that. It wasn't perfect in that direction. And it'll be longer, and that'll be the resultant vector. Okay? So this is how you do 2.0. Okay? So try B and C, and actually do A. Retry A and do B and C when you do this. Okay? We're going to do the same exact thing for 2.0. Intro to Electric Fields. This is the second page, and this is part 2, and this is number B on this. Okay, so we're going to do the same exact thing. Okay, again, I'm going to mark these with different colors. This negative Q, I'm going to call that blue. The number 3Q down there is going to be green. And that positive Q right here is going to be red. So we're going to do the same thing that we did in the other one. All right. So this A is really close to that red positive Q. So I'm going to draw a large field vector to the left, away from that positive Q. The blue Q is going to have a shorter electric field vector pointed up and towards it. Okay, because it's further away. In fact, very far away. And the green one is also negative, so it's going to have an electric field vector pointed towards it. Okay, kind of looks like the flux capacitor. All right, and maybe I'll not draw that so large. All right. Well, now I'm going to add those vectors together. Okay. So I have red to the right. And it doesn't matter the order that you do it. I have blue, which is up and to the left, a short amount. Up and to the right. And then I'm going to add to that, this is interesting, and then I'm going to have a green vector down and to the left. Okay? So this is a really interesting one I chose. Because these two vectors, in a way, are nilling out part of the red vector. because I started here, I walked 2 huge steps to the left, walk a step up and to the right, and a step down and to the left, so I'm ending here. So this is the finish. If this is the start and this is the finish, then my resultant vector is going to be directly from start to finish. That means the resultant vector here is going to just be just to the right. Okay? So we're using the same vector. You're drawing the electric fields at each one of these. Okay? And what you're also going to do is determine where the electric field is going to be 0. Okay? And obviously the electric field is not 0 here, because when you sum up all of these vectors, you get a vector. When you get the electric field being 0 here, when you sum those vectors, they should come in on top of each other. I'm guessing electric field is going to be pointed towards this one and away from this one, and then towards this one a little bit. So I'm guessing that the electric field, I don't know, the electric field is not going to be 0 here at A, B, or it might be at B, it might be at D. Let's try this. I'm guessing the electric field is going to be 0 at D. Let's try it out. And I'm going to show you what happens when the electric field is 0. So I'm going to draw a large vector up and towards that green guy. Now the blue guy, which is really far away, is also going to have an electric field pointed up and towards it, but it's going to be a very small amount. And the red guy is going to have an electric field pointed away from it, but a little bit bigger than that blue guy. So yeah, I don't think actually the electric field is not going to be 0 here. So yeah, this is a really interesting problem. Let me check something. Actually, I think I made a mistake with the size of my red vector here. So this, okay, so let me backtrack a little bit. This guy right here at D, let me show you what I'm talking about. I think I made a mistake at A. And so what I'm going to do is actually erase all those. And I'll show you why I made a mistake. And this is just, it goes to show you, you have to kind of watch, you have to really pay attention to your estimates of stuff. Okay. So it's good that I'm making a mistake here. Let me add these together. So I'm pretty confident in my estimate of the size of these vectors, right? So I'm going to start off by adding the blue vector here. And I'm going to add to that blue vector, and again, doesn't matter the order in which you do this. I'm going to add the green vector to that, and so I'm being consistent with that. Now the red vector is going to be a size somewhere in between the blue vector and the green vector. And so now I'm going to add to that the red vector, which is bigger than the blue vector, but not quite size of the green vector. And so by adding those together, you started here, you ended here, so the resultant vector is going to be north or upwards, right? So that's the resultant vector. I think I made a mistake with the size of that red vector. Or actually, rather the size of the green vectors. Because if the red vector was this big, the green vectors and the blue vector should be kind of large too, but not quite as large as that. Okay? So I'm going to point this guy up and to the right there. And I'm going to do the green vector pointed towards that charge. And so here's where I think I made my mistake. I think A is actually where the electric field is 0. So if I draw my red guy just to the right, I'm going to add to that the blue one. I think that was the order in which I did it. I added that vector, the blue one, right? That was about the same size as that one. That red vector is the same size as that. The green vector should add on top of that. Yes. So notice that the electric field, yes, this is true. So if I notice the electric field, if I start here, I walk to the left 2 spaces, I walk up and to the right 1.5 spaces, down into the right 1.5 spaces, then I'm ending here. The electric field is 0 at this point right here. And the reason why I made a mistake in the first place is I basically underestimated the size of the green and blue vectors. So it should have been right on top of each other. So anyways, I hope you enjoyed this. This is actually the this is going to be the resultant vector. That should have been red, black there. So this is how you do addition of vectors. And so this first tutorial is really just kind of getting you in a sense with drawing vectors, but also estimating them spatially according to this equation. Okay? Let's talk about the calculation of the electric field. Okay? So if you want to measure we've been doing this type of thing where we're estimating the electric field vector size spatially. This whole time we've been estimating the electric field vector size based on our just abstraction of 1 over r squared. You know, the size of the vector drops off by 1 over r squared, right? When it's further away, it's a little bit smaller. So now let's concentrate on just the quantitative part of the electric field equation, which is the Coulomb constant, 9.0. So that K right here, which we represent a small k, with a small k there, which is going to be 9.0 times 10 to the 9th newtons meters squared per coulomb squared, right? So that hasn't changed. But since we're calculating the electric field due to a single charge, right? We're not doing force, so this isn't 2 guys. This is just we're just doing the electric field due to 1 guy, right? So we just got our Q, and it drops off by 1 over r squared. Okay, so we're going to practice creating equations doing that, right? So this is a really good practice. What you're supposed to do is you're supposed to draw the electric field at the dot, okay, and that you're supposed to then create an equation in terms of K, small q, small r, and then and create an equation to represent case A, case B, case C, case D in terms of K, Q, and R. And then we're going to then estimate there's from largest to smallest. Okay? So go ahead and pause the video and try this out for yourself. So try to draw a vector at let's try to just do A together. Draw a vector. Well, which direction do you think the vector is going to be, the electric field vector is going to be at the black dot due to this positive Q, a distance r away. And then after you're going to do that, then I want you to create an equation to represent the magnitude of that in terms of K, Q, and R. So try A right now. Pause the video, please. And we're back. So the electric field at A is going to be pointed away from the, at the black dot for A is going to be pointed away from it. And I'm going to just say it's going to be this size. All right. I don't know right now relative size. I'm sure it's going to be different. The size of that vector is going to be different based on these other dots. Okay. And so it's going to be pointed in the positive x direction. Right. We still have a coordinate system, plus y, plus x. So it's going to be pointed in the positive x direction. And that electric field, these are all going to be in one dimension, by the way. So the electric field is going to be pointed in the positive x direction, and that is just going to be K, Q, all over R. It's a distance R out, and then you're going to be squaring that R. Okay, remember to put your brackets around R. That'll remind you to put whatever the distance is in here, and then you'll square that. And so that equation is now going to be, that vector is now going to be KQ over R squared. Okay? Now let's do D really quick. D is also a positive Q, but it's twice the distance. So it's twice as far, and you know the electric field is going to get weaker the further out it's going to get. So do you think that field vector is going to be, the field vector for D is going to be larger or smaller than it is for A? What do you guys think? So electric field at A, is that vector going to be greater or smaller in length than what you would think at D? Well, so electric field at D is going to be pointed, it's also going to be pointed away from it, so it's going to be pointed in the positive X direction. And it's going to be positive, and then we're going to put K, and we just have our Q here again, it's a positive Q. But that distance is 2R that we're squaring, okay? So that's going to be, I'm going to multiply this all out. That's going to be positive KQ over 4R squared, or in other words, 1/4 KQ over R squared in the positive X direction. Okay? So in fact, this electric field here vector is going to be it's going to be a quarter the size of our original vector at A. Okay? So that electric field at D is going to be the quarter of the size of the electric field at A. It's going to be in the positive direction. Okay. Let's do C. Why don't you pause the video and try C? And actually, before you do C, I should hold on a second. Estimate, do you think C is going to be larger or smaller than A? And by how much? You know, is it going to be 4 times bigger, twice as big, the same size, a fourth the size, half the size, or a fourth the size? What do you think? Well, it's got twice the amount of charge on it, and it's the same distance. And since Q is directly proportional to electric field, I'm guessing, well, what do you think? Why don't you pause the video and try it yourself? Okay, we're back. I'm guessing it's actually twice the size of EA. So I'm thinking E sub C, which is pointing in the positive X direction, is going to be equal to twice that size. Let's see, K times 2Q, and it's all over R that is being squared, and that's equal to 2KQ squared over R squared in the positive direction. So it is twice the size. That's interesting. B is an interesting one. What I was thinking interesting is B is hard for me to do. Well, you're increasing the charge by twice, but you're also increasing the distance the same, twice the distance too. So you're doubling that, but since you're squaring that distance, it's going to be dropping off by 4. So you're going to have 2KQ squared over R squared, but also you're going to have a fourth this. So it's kind of B. I guess what I'm saying is B is a combination of C and D. So I'm guessing it's going to be something like 2 over 4 KQ over R squared. Well, I don't want to draw the vector just yet. I'm going to do the math first. But I'm guessing it's only going to be half. It'll be half the size of this. So a fourth. I'm going to put a fourth of EA here. This is twice EA. And my guess is this is going to be a half EA. So I'm thinking EC is going to be a half EA. All right. So this is EC pointing to the right. And that is going to be equal to K, and you put your 2Q in there, and the distance is twice the distance, so I've got to put 2R and square the 2R in the parentheses. I'm going to multiply the top part out, and I'm going to get 2KQ. Did I put squares on things? I'm so sorry. Jim. It's just a square on the bottom part there. Sorry about that. And this bottom part is going to be 2R that I'm squaring, so that'll be 4R squared. And it's pointed to the right. And so that'll be 2 over 4, which actually I was right in my guess. It's going to be half KQ over R squared. All right. And basically this is how you go through estimating the size of those vectors and actually quantifying it. All right. Well, that concludes the very first part of 2.0, electric fields. I hope you got a good handle of how all that works, right? So how electric field vectors are pointed away from the positive and towards the negative, and it's at a tangent to the surface, and that the electric field line density is proportional to the strength of the electric field, which then the length of the electric field vector is proportional to the strength, and that's represented by KQ over R squared. Okay? All right, bye.